curve, and we're going to add some extra details to it. So the red line is our DC transfer curve. So that's, that's the same as what we had here. This was the ideal, but now we're going to have a little more realistic. There's a couple of points that we like to identify, okay? First off, I said, when you're at the top of the curve here, or at the bottom of the curve here, that's great. You look like the output is a 0 here, or it's a 1, and it looks like a solid 0 or a solid 1. And in the middle here, we don't like it. And we need a way to distinguish between when do you come into that region versus these other two regions. And the way we commonly do that is we say, well, let's take the slope of this curve. And when the slope equals -1, that's the dividing line. And it's -1 here, and it's -1 there. And so to the left of here is a good 1, to the right of here is a good 0 output. But in between here, that's the defining line. And those lines where that happens, we give them a name. We call that, if we extend this down to the x-axis, when the input is a logic low and the output is a logic high, that's V input low. And this one here, we extend it down to the x-axis, we call it V input high. And basically what we're saying for V input low, as long as the input is down here in this region, so that's the maximum voltage you can have that it looks like an input low in this case, and the output is high for this inverter. So the maximum input, which we recognize as a low voltage. Anything in here is a low voltage, and this is the maximum, because any bigger than that, you enter in this undesired zone. And likewise for V input high, it's the minimum value looks like a high. Anything in here from all the way to VDD down to this V input high looks like a input logic high. And if it's below that, then it's in this undesired zone.
I just had a quick question. If there's a thing of noise, there would be a sharp kind of spike, which would cause a slope of higher than -1 or whatever. Would that be considered like a all of a sudden a 0?
What would typically happen, like let's say you had an input that was here, and you would say, oh, this is a great input. It looks like a logic low. And somehow something coupled through and you momentarily got a spike, though you momentarily went over here and then back here. Or worst case, you momentarily went here and back here. Then it could cause your output to glitch and go low temporarily. So the noise, assuming this is noise, can make what's a good logic low look like a bad logic or even a logic high. So noise is bad. That's the bad thing about noise. Can temporarily make your logic low or high look like the opposite or unknown. Okay. So for a CMOS circuit, these have V input low and high, and when when your output is the maximum value, we're going to call that the output high, and when it's the minimum value, we're going to call that the output low. Okay. And also we have, if you take a straight line from this point and go out, and it's got a slope of 1, that's where V out equals V in. This has a slope of 1, V in and V out are the same. The point where it intersects this transfer curve, we call that the switching threshold. We're not going to use that much, but just so you know, that's what it's called, the switching threshold. That's basically, ideally, anything above, input above this switching threshold looks like the output low, and anything below it looks like output high. But that's the dividing point. But we don't want to be in this area at all. This is like kind of a bad zone. But that's kind of like the center of that zone, if you want to think about it. And this is just showing our inverter. If you want to find the slope of this line, if you connect the output to the input, then V in and V out, that actually generates this line. And then this is our inverter now. We have these new 4 terms: V output high, V output low. Oh, this should be V input. It should be I. A different color. Oh, I don't know. This is V. These are backwards. It should be V input low and V output low. And the output ones are output high and output low. Okay.
Wait, so it should be V input low and V input high, and the other one should be V input.
Let me redraw this. This inverter should look like this. Ooh. Gotta draw slow. This tool is not good at drawing. this says V output high, V output low. These are your output terms. And on the input, this should be V input high and V input low. So that those can't see the red over the red, but these ones are wrong. X. Can I X? Oh. Blue, 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 blue. X nay on that. This is what it's really, okay? Let's go back to here. Now, if I want to look at these V input high and V input low, another way to look at it is this picture here, okay? And what we're going to talk about is what's called the noise margin, and it's related to the reliability of the circuit. So on the left here, we have the output high and output low, okay? So these are the output values that we get. And this is the power supply. Let's say that's 1 volt, maybe. I don't know. This is 0 volt, that's the ground. We really want this output high to be as close to 1 volt as it is, but let's say it's not all the way to 1 volt. Let's call it some value here. And we want the output high to be 1, we want the output low to be 0, but maybe it's not perfectly 0, but that's as low as it gets. And on the input side, on the right side here, we have an input high. We said anything above that looks like an input high, and anything, and a V input low, anything that looks like a low. And typically the input high and input low are in between the output high and output low. And so we can draw this thing like this is input high and output high. The difference between those, we call that the noise margin, in this case for the high signal. And the difference between the input low and the output low is the noise margin for the low. And then the red part is the undefined. Anywhere between V input high and V input low is undesired. So this red zone with the depth, that's this zone right here between V input high and V input low. So what is this saying? It's saying that, okay, let's back up here. Here was our inverter and output high was 1. And so as long as input low was, in case of inverter, was below this value, it's fine. But if we got up above here, it starts looking undefined. We don't see it, right? So we want to keep, for a low, we want to keep it down here. A high, we want to keep it up here. And well, just back up. Let's back up. Just realize I'm talking about 2 inverters, one inverter driving another. So actually, maybe it's better to draw in this picture. So let's say this output is coming out of this inverter, right? And it's coming out as a high here, and it's close to VDD, right? And for this to recognize an input high, maybe it's at, say, the input high is 0.7 volts to recognize a high. This output will go 0, but this output is 1.1 volt, and this says an input high looks like 0.7. So this is 0.7, and this is 1 volt here. Then we don't have any problem. This looks like a 1. It looks, it's much higher than the 0.7. So this inverter will look correctly, okay? Work correctly. And the difference between them is the noise margin. But we know that even though I'm trying to bring out a 1, because of all this ground bounce, there's going to be noise on here, right? And so I've got, in this case, 0.3 volts of noise I can handle, and it still will look like an input high. So I've got lots of noise margin. So the noise margin is the difference between the output high and the input high. But if this were to drop, or this were to go up, I would have less margin. Then the noise might cause this second inverter not to work correctly. Okay, so that's what this whole idea means. And then we have the same situation on the bottom. When I'm driving out a 0 out of here, this has an input maybe the input low is 0.3 volts. Then, yeah, there's a bit of ground bounce on the 0 volts coming out of here. No problem. But if we have more noise than 0.3 volts, then this inverter doesn't work, the second inverter. Anyway, those are the noise margin. So it turns out for CMOS, V output high and V output low are typically close to 1 and 0. And these V input high and low, if we make this slope really steep, they're very close to VDD over 2. So they're very close to the center, and we get a lot of noise margin. Okay. And that's good. We can tolerate all this noise coming from the other circuits, and we don't have to worry about it. For example, if we looked at, let's go back to our old example that we did really early on. Let's say we look at our common source amplifier or inverter that we did before, right? And if you were to draw the transfer curve, DC transfer curve for this, which you probably did a long time ago. So this is V in, this is V out. What does it look like? When V in is 0, we're at VDD, right? This is VDD. And as the input increases, so as this goes towards 1, what's going to happen is we're going to start drawing current to this resistor. And it's going to start going down. But we're going to see that it never goes all the way to 0. It kind of looks like that, the DC transfer curve, because there's current going through this resistor. And as long as I have current going through this transistor here, and if I looked at let's say VGS equals 1 volt here. And this is VDS, and this is ID for this transistor. As long as the current is not 0, we'll always, maybe this is the DC current here. It's 1 milliamp or something. I don't know, whatever it is. VDS never goes to 0, right? This is our VDS. As long as we have to get current to 0 to get VDS to 0. So I always get this VDS. Right? That VDS there is the same as this in terms of like the characteristic curve. So I never get to 0. So what does that mean? That means this is my V output low. My V output low is not 0. It could be 100 millivolts or something like that. So if I go back here to my curve, this V output low is not 0. For CMOS, it's V output low is here and V output high is here. But for this RTL circuit, this V output low is high. And so now this noise margin is much smaller. So a circuit like this, not only does it dissipate power, but it's not reliable because it's more susceptible to noise inside of it, which was another limitation of it. This is like a secondary thing, but it is a problem. So CMOS circuits are great because these noise margin terms are huge. Like they're almost equal to VDD over 2. Ideally, that's the largest it can be is VDD over 2. You have half the supply voltage is noise margin high and half is noise margin low. Well, that's 9:55. That was a long explanation, but I hope that made sense. And the noise margin are defined by these equations. Noise margin high is V output high minus V input high, and noise margin low is V input low minus V output low. Any questions? No?
Sorry, could you just reiterate? So for what part has a bad noise margin or bad accuracy, and what part has a better noise margin?
Why does it?
Yeah.
I said this RTL circuit here has a bad noise margin because the output never goes all the way to 0.
Oh, okay.
And that meant this V output low was not 0. It was like maybe 100 millivolts or something, depending on how much current you're putting through it. For CMOS, this V output low is 0.
What would be a average noise margin then for a CMOS?
For a CMOS, like it's close. Like this switching, these V input high and low are very close. There's maybe like if this was a 1 volt supply, this would be like 0.4, and this would be like 0.6, maybe, or even closer. But basically, you have like 400 millivolts of noise margin on each end for a 1
Okay,
volt
thank you.
supply. Basically, this is what we call static CMOS, has the best noise margin of any circuits. Basically, it's the best. And so, getting back to our picture here, where we were saying, oh, we're interested in this reliability, super reliability of standard CMOS. It's very robust to noise tolerance. And so we really like that. It makes it much easier to design our circuits. We don't have to worry about the noise very much. I shouldn't say we can totally ignore it, but generally speaking, it's not a problem. Other circuits, not so much. Okay. Okay, that's it for today. So we'll see you next Tuesday.
Professor,
Yep.
I have a somewhat unrelated question, but
Okay.
over the